Thanks, Yassi. So I'm going to talk today about integrated research infrastructure. This is a little bit of a, I think, different modality than you have been looking at for the days that you've been here. So you've been here learning about the systems that we have, how to use them effectively, including Polaris, including Aurora. It's a nice artist rendering, but you guys saw the real thing on a tour, so that's fantastic. Maybe what's not evident to you after the last few days is that sounds too loud, is a progression of machines that we have been on, right? So ALCF has had systems going back to 2004, and we've been in this progression where we're steadily upgrading our machines every 5 years or so. And we will continue this. And so you're learning about Aurora today. We will carry that machine forward and do great science with it. And this is all happening at ALCF, which is a user facility. You're all users. Hopefully you'll be users for a long time. All of the computing facilities are user facilities, meaning that we operate these machines for people to come and do their science on our machines. How many user facilities do you think DOE operates? Other than computing facilities? Not sure. 24 user facilities around the country doing all sorts of different types of science. These are aside from the computing facilities. All of them are experimental facilities that have computing needs, and some of them are at the top of the distribution in terms of how much computing they require, and some of them have smaller computing needs. The ones that are at the top have been, to the largest extent, been operating within computing that they have local to their facilities. Some of them are upgrading, just like we're upgrading, and their data rates will increase and their computing needs will increase. And so they'll begin to need computing that's beyond what they have local to their facility, and they'll need larger computing, and they'll need to be able to do that in an easy way. I had a conversation with someone at a light source a few years ago who said he liked to do all of his computing local to the light source, because if anything broke, he was in complete control, he could fix it, he could get his computing back online, and everything would be working again. And I asked him, what if you needed remote computing that was larger than what you have, and it was transparent to use, and it was reliable? Then what would you do? And he said, then I would do all my computing remotely, because then if something breaks, I wouldn't have to fix it. Which I think is a great sort of flip, right? It means that if we can make it simple for them to use remote computing, they'll do it. They'll give up this control that they need over their resources because they know that they can rely on the remote resources and they won't have to fix it themselves, okay? But that's a challenge. So this is all about integrating facilities like ALCF with experimental facilities. And we've been doing this for a long time because we anticipated this. So in 2015, Christine just talked about Balsam. We instantiated the Balsam project so that we could integrate Atlas computing, which is a very different model from supercomputers, with, at the time, Mira. And we carried that forward through several other projects. Fusion, which I'll talk about in a little bit more detail. Nuclear physics, which was supported by an ADSP project years ago. LIGO, done things with BES and electron microscopy. More work with fusion. There's work with light sources, which I'll talk about, and with the DUNE project. So this is a project that we did shortly after we instituted Balsam for the Atlas workload. And the case here was that at the fusion facility, they're running an experiment, and they take a shot every 20 minutes. And every time they take a shot, they need to run some analysis on the data, use that to calibrate for the next shot where they're trying to contain the plasma in the tokamak, and then apply that calibration so that they have that in time for the next shot. At the time, they were running this analysis on a machine local to their facility, and it took more than 20 minutes to run, which means that every time they took a shot, the next shot, they would make some adjustments for the next shot, but they did not have the analysis results from shot 1 to inform shot 2. It went to shot 3. And so they were always losing one shot in terms of how well informed they were. We worked with them to integrate analysis. At this time, it ran on Cooley, which is an analysis cluster. Cooley's still around. I don't know if you learned about Cooley in the last few days. It's a little bit old. We had a reservation on Cooley for a week while they were running their experiment, and every time that they took a shot, we started a job via Balsam on Cooley. It fetched the data from D3D, ran the analysis, and pushed the results back to them so that they could have that in time for the next shot. And you can see this, I just blew up this timeline of their experiment. In the bottom part, you can see that we finished this analysis on Cooley in time to return the results back to them. If you've seen D3D, you'll see that there's a control room with huge displays and people conducting their experiments and trying to make decisions about what to do next. In this case, they had the details that they needed to inform the next shot well in advance of the time when it would take place. In addition to that, because we were using more computing, we also ran the analysis at 16 times the resolution. So they got better results faster. And if you think about the fact that they had that analysis result to inform every shot instead of every other shot, it's in a sense 100% increase in the throughput or the productivity. We went from that example into looking at how we could power light source computing. Again, because we anticipated, excuse me, that they would be outstripping the computing that they had available to them. We talked with 4 light sources, and at the time our machine was Theta. We still have Theta. I think you learned about Theta. Maybe you learned about Theta GPU. I'm sure you learned about Theta GPU. We worked with the light sources to do something similar, right? To take workloads that they had and as soon as they had data, transfer the data from their facility. These facilities are all over the country. One of them is on campus. And do the analysis and then make the results available to them again. And you can see here estimates of the workloads that they expected to have by 2024. We simulated this, so we asked APS for as many data sets as they had. They gave us a couple 100,000 data sets. We combed them, we cleaned them. We had about 100,000 data sets that were valid, that we could run easily. And we selected from among them for this test, the largest one, which is a 40 gigabyte data set. And then we simulated that if they had taken that data and transferred it to ALCF and analyzed it and pushed the result back, if we could do this from 3 facilities at a time, could we keep up? And so you can see from the plots that we could keep up. We continuously transferred these 40 gigabyte data sets, analyzed them, and sent them back. We did this for 48 hours. At the light sources, they run experiments for, well, users, like you get an allocation here, users get beam time at a light source. It's typically 2 days. They bring teams of people. Some of them don't sleep much. And they run their experiment for a couple days, and they collect data, and we wanted to simulate that same experience. So we take their data, we continuously transferred from the 3 facilities to ALCF, analyzed, push the results back to them, showing that we can do this. If you look at the numbers on this plot, you might say, well, that's some really slow networking. and that's true. That's true, and there's a lot of reasons for that. We didn't optimize the network. We used Globus for throughput, for transferring data, and in some cases, you can make optimizations if you have a single large file, like 40 gigabytes, or if you have many small files, you can adjust how you transfer so that you get better throughput. We learned some lessons. We made those optimizations in Balsam so that we could achieve better throughput. So that was from 3 light sources to ALCF. And then we thought, well, that's great, but we really have to power these by all of the compute facilities. And so the goal was to be able to do the same thing from these light sources to now multiple compute facilities. We set up the same approach and ran a similar experiment, in this case, between 2 light sources and the 3 compute facilities at the time. And you see some similar plot of the throughput that we got running the same thing. We ran a couple different workloads, and the setup was slightly different from the first case. If you're interested in the details, I can point you at papers. Around that same time, we started having conversations with DOE about integrated research infrastructure. It wasn't called that at the time. We were just talking about the need of all of these experimental facilities having to run their analyses in a remote fashion. And so if you look back at, it took us some time, a lot of discussions to reach maybe what this should look like. But this is kind of capturing where we were and where we were trying to go. Yeah, on the top, you see an experimental facility. And if they wanted to integrate with a compute facility, there's a variety of things that they have to accommodate to actually use a compute facility effectively. And that can be complex. If they want to then do the same thing at another compute facility and a third one, then they have to go through all of that same complexity, or sorry, different complexity for each site. And that's a challenge. It takes time. It takes time away from them doing science, and that's not what we want. We should make it simple for them. So if we had a single way of them interacting with the compute facilities, then when they integrated with one of them, they would then have access to all 3 of them. All right, ESNet is there too, but ESNet's not computing. And then if we think again about the 24 experimental facilities, it's not just one, right? We get some compounding factor from that so that they all only have to do that work once. Maybe there are patterns among them so that the work is done once and it is easily reusable by multiple experimental facilities. This is a slide from Ben Brown, who is the DOE program manager who has been championing the IRI effort for a long time, and I think it captures pretty much all the things that I've just been describing, right? The thing I like about this slide is that we have this sort of coming together of the experimental facilities and the computing facilities. And you would think, maybe from the way that I laid it out on this slide, that the computing facilities are at the center and the experimental facilities are around the edges. And that's the story we need to tell. A lot of people don't like that story. A lot of people don't like that the computing facilities are at the center of the world. And I agree with that, right? In this diagram, who's at the center? The people doing the science. That's what it should be, right? I think that's the point that is important here. And maybe I should have learned from when I made this slide 3 slides ago. But anyway, we're telling the right story, I think. So in addition to the white paper and a few other artifacts that have come out of our discussions over the past few years, there is now this IRI report. In it, you will see probably a lot of things that look similar to things I've said, or some of the diagrams I've shown, because the report itself is actually fairly thin. There's a lot of good content that summarizes everything that I think we've been talking about, and then appended to it is a bunch of slides, a bunch of documents that really, if you go to get it and it's like I don't know, a 60 or 100-page report, you might say, I'll read that later. Leave it in an open tab like we all do, right? But just look one level deeper, because really if you read the first 10 or 15 pages, you'll get the gist of the whole thing, and then you're done, you can close that tab, which always feels like success. But the point that I would make here is that out of this, we came up with sort of these science patterns and these practice areas. I always think about the science patterns, and I always forget the practice areas. But okay, maybe it's because I can remember 3 things, but I can't remember 6. They're all important. The point is that the time-sensitive pattern is the one that I've been talking about and that we always talk about, right? Everything is about time to solution. Everything is about time to science. And that's why it's at the top, in my opinion. But there's also data integration intensive. You've all been talking for the last 3 days mostly about simulations. Okay, not just simulations. Also big data. Okay, big data. We don't say big data anymore. We say data science. But data intensive computing is different from the simulations that we have typically run on our systems. And many of us are doing that kind of work now. It means that instead of taking some parameters and simulating and writing out a petabyte of data, now you're bringing in a petabyte and you're reading it instead, right? We're all familiar with that pattern. And you've talked about ML. So ML is same sort of thing. So that's the data integration intensive pattern. And then long-term campaign is just saying some projects don't do a single experiment, analyze the data and are done, or don't run for only a week and they're done. Some of them are conducting surveys of the sky over years and then analyzing that data over years. And how do they manage petabytes of data at one or multiple compute facilities over the span of years as systems change, right? We talk about architecture change. We don't talk about tape storage change so much, right? But the data has to persist somewhere. And these things are not mutually exclusive, of course, right? I mean, people who are doing long-term science do also care about the results they're getting this week, right? They do have a lot of data. It's just that for every project, it's a little slightly different mix of these 3 patterns. I'm going to not talk about the practice areas because there's 6 of them. I never remember them. They're standard things. They're things that we've been talking about. Okay, maybe we should talk about them for a minute. User experience is important. It's very easy to get frustrated with getting things working on a system, coming back the next week and it doesn't work. And you're like, is that me? Or did a dependency change out from under me? I know I have that problem. I talk to a lot of people who have that problem. Okay. We will have to deal with things like security, right? If you're talking about experimental facilities and people running jobs over the course of 2 days or a week, it might not be the same person who's collecting the data, transferring the data, running the analysis. It very likely will be a team of people. And we can't share accounts in DOE. You can't share your account with somebody else. We're trying hard to understand how we can support a team using an account in a constrained fashion so that people can shuffle in and out of the experiment and all of the work can continue without relying on the one person who went away to sleep or got sick or got hit by a bus or whatever it is. Workflows is an important thing. We've been talking about workflows and how to automate things. Excuse me. Scientific data lifecycle, okay. I won't talk about all of them in detail, but that's important. And being able to do things across multiple compute facilities is important. So I talked a bit about compute facilities, experimental facilities, and about how we accommodated some experimental cases, and about the IRI program. The IRI effort is a thing at the level of DOE, and we have been working with colleagues from NERSC and OLCF and ESNet and scientists all over, and some of you may have been involved in discussions that involved your work and how it could be made easier, in the context of multiple compute facilities. Some of you, it looks like, are either very attentive or giving me the furrowed brow, like this is a strange thing, I've never heard of this. So clearly there's a distribution of familiarity. But while we've been having these conversations about IRI and what it should be and what all the different facilities think it should be, we have been pushing forward ourselves, as I mentioned. And so now the project that we are pursuing IRI under is Nexus. So there's a Nexus webpage. The Argonne Nexus project has goals that really align directly with IRI. It's not an accident. Turns out that if you talk about the work a lot, which we've done in the context of IRI, and if you do the work, which we've been doing in the context of Nexus, these things align, okay? It's fortunate that it works out that way, because sometimes it's not the case. But in terms of what we've really done, a big part of what we've done is to work with the tools that Christine laid out in her presentation. We talked with Parcel, we talked with the Globus team about Globus Compute, and we take our own experience with Balsam and carry it forward into what we think would be a solution for experimenters. And it's not just about workflow tools, that's what those things touch on, but also, if you're on Polaris, you may have encountered the demand queue. The point with the demand queue is that there are 500 plus nodes on Polaris, and some number of them have been pulled off and put in a demand queue for users who have on-demand needs, like the experimental facilities, to come in. Their jobs will take priority in the demand queue on that chunk of nodes. They'll run as soon as they hit the queue. What happens to people who are using those nodes? People who are using those nodes were running in the preemptible queue, and they recognize that they might be able to get those preemptible nodes quickly. They might be able to get one node for longer than they would expect, but at any time their jobs could be vacated. They're gone. So if that means you're checkpointing regularly, it's a good use case for you. How do you get access to the demand queue? Well, if you're in an experimental facility, then we can have a conversation. Service accounts is something I touched on a bit. So that is the idea that we can give an account to, say, an APS beamline, or a facility that brings users in individually. So we're not just running jobs for one user, we're running it for one beamline, for example. I know that you have probably talked about the Eagle file system and Globus sharing that's enabled from the file system. In this case, you can designate a directory that should be publicly accessible to any person with a Globus credential to fetch your data and move it to their own facility. They don't have to authenticate to access that data. Well, you can make it so that they do have to. You can authorize particular people, or you can make it completely public. I mentioned the Globus infrastructure, the ALCF Community Data Cooperative. I have a slide on I'll talk about in a minute. And then dedicated web applications is one step beyond the ACDC portal. ACDC says, how can we make data easily findable and view the metadata, make choices about what to download? Dedicated web applications are more like, I need something that is a little bit deeper into my own application domain, and maybe do some analysis, maybe make some more constrained selection of the data that I want so I can transfer it off to my own facility. So we bring those pieces together then in Nexus to look at how we automate work from light sources. So there's a very simple diagram. We take data from at the APS. APS uses a data management system, and as soon as data lands in the data management system, there's a trigger that says that data is ready. It should ship off and go to ALCF, and we should submit a job to analyze it. And it, of course, runs in the demand queue. When it's finished, the results are pushed back to APS for them to look at. They can also, of course, use Jupyter, which I know was talked about during this workshop. So we have the data sitting on Eagle, and you can access it with Jupyter using maybe a pre-constructed Jupyter notebook for that data or that analysis, and immediately view it while the experiment is going on. This diagram is a little bit more complex version of the last one, but really just highlights the fact that on the top, it's sort of the way that people would have done things previously, where individual users come in. And just to clarify that a bit, when users come in and they have their time at APS, this example is APS, they're known to APS. They're not known to ALCF at all, right? So if they wanted to do analysis at ALCF, they should prearrange that. They should get accounts. You're all familiar with the account process for getting on ALCF systems. Not always easy, depending on who you are, where you come from. It would be nice if it was easier. There are a lot of users at APS. We don't necessarily want to give an account to absolutely every APS user who shows up so that they can get on our systems. So the way that things would have been done before is this approach, where the person arrives at APS, gets an ALCF account, sets this up themselves. They are responsible for running all their own jobs. They face the problem that if it's time for them to go home and sleep because they've already worked for 12 hours on the beamline, they really should pass that off to their colleague, who hopefully also has an ALCF account and sets things up for himself, herself. And so you can see the inconveniences in that process. So on the bottom, it really is just using a service account, like I said, and it's set up once, and things can just run in an automated fashion from that point on. So a lot of lines and colors on the slide to indicate that it's easier to use a service account. So does this work? The APS is dark right now. So it's undergoing an upgrade. I mentioned a lot of the experimental facilities were undergoing upgrades. APS is undergoing an upgrade. Huge upgrade. Really interesting. If you go and, there's a lot of detail online about the upgrade that's being undertaken, how much work, how much money is going into this, how much more data will come out, the new experiments that will be enabled. So it's really interesting. And what we have been doing is setting this up at multiple of these sectors, right? So that the way that the APS works is that the beam comes off at these sectors all the way around the ring, and individual experiments are distributed around the ring, and they can make their own decisions about how to support their users, right? It's really not that the APS is supporting all the users. It's that the sectors support the users. They run different types of experiments. I want to do experiment X. I go to 2ID, for example. The people who run 2ID can choose to set this up. They get a service account. They have this set up for their users. They have this integrated into their data management system so that this whole flow takes place without their users having to care about it. And multiple of them have done it. So the bold green sectors on the ring are in production. Now, when I say in production, what does that mean if they're dark? It means that they were in production before the APS went down this fall. The ones in light green in regular font are running. They have it all set up, it's ready to go, but they did not run before the APS went down for the upgrade. And then the ones in yellow are ramping up now. They see that this is coming up and they want to engage and make this possible for when they come out. I made this slide probably 2 weeks ago. It's probably out of date. So what do they get? The point is that once they've set this up and things are running and things are automated and everything's working, what does that look like for them? So you're familiar with Globus from the standpoint of transfer. Globus has an array of tools. And when jobs run, when transfers take place, you can go to the website and you can see the transfers you've scheduled, how much progress they've made, what problems there were, if any. You can monitor the transfers. The same thing is true with compute. So we see, for example, job flows that were begun, and you can see detail of the flow, and if you click on that, you can go down into more detail. In this case, we can see all of the different steps in the flow. So we talked about Globus Compute as a thing that is, I have a job, I want to run a job. A flow is generalized for actions, and actions can be data transfer, they can be running a job, they can be publishing the data to some public location, it can be getting a DOI for data that they want to be able to refer to in the future. All of these things come and can be monitored through this, because if you have an automated system and then something doesn't work, you kind of need a way of understanding what it did and what went wrong. I mentioned ACDC. ACDC is a site where we can publish data, and it can be made publicly available in a way that gives you a little bit more information about what's there, right? If I personally am a terminal guy, right? So I would want to go to the terminal, and if and some of this detail would be in my head then, and I function that way. It works for me to have all the metadata in my head when I'm looking at data sets. Most of the time, it works for me. I can't get this data via LS, or I can LS and grep and get all this stuff if I know what I'm looking for. If I capture it in an interface like this, it's easy to find. I can find it. If you wanted to access my data and I've made it public, you could find it and probably make sense of the metadata. And you could choose to download it. You could choose to analyze it. So ACDC is a way for us to make that possible. And then there are other approaches. I mentioned having an approach where you need something that's a little bit more specific to your data. You need to extract metadata and have that more integrated into the search and into the analysis that you'll do. So sometime back, we created a portal for cosmology data sets. And in this case, you see multiple models with different sets of cosmological parameters. And you can make choices here about which of these models you want to download and which types of data you want, whether it's particle data, halo data, right? There are different levels of data, some processed to some degree, some larger, some smaller. Give me all the particles. Now I'm transferring a terabyte of data to my facility. Maybe that's too much. Maybe if we have integrated analysis tools into this sort of a portal, then it's not too much, right? Because I can say, I want to reanalyze that terabyte of data, just submit a job for me, don't move the data, give me the results back in a place that's available to me. Maybe it's in the ACDC, maybe it's somewhere else. It's just sitting on Eagle, I can log in and I can access it. So this probably looks like a little bit of a left turn or an add-on at the end of all of this IRI stuff that we've been talking about. But if you think about data sitting on the systems and how we can share it and how we can make it available and all the tools that we've talked about, they all can come together to support a thing like this, right? So I think it would be short-sighted to say, we have a solution, we're using it for the one problem that we identified. If we have a solution that applies to other things, like this, for example, then I think it's a proof, actually, of the solution, that we can apply it outside of its original design. And I'll end just with, again, a reminder of this report. If you're curious, please don't click on the link there that I forgot to put on the slide. You can easily find this report. But if you have any questions about Nexus, which I described, I'm happy to talk to you about our efforts here at ALCF. And if you have any questions about IRI, the process, what is going on there, what it could do to help you with your science, we need use cases like that to help elaborate what we're doing so that the result is more applicable to more people. So I'd be happy to talk with you about that too. I started late. Maybe I have 10 minutes for questions, or yeah, maybe I have some time for questions. Yes.
This is very exciting stuff. It sounds like progress. But one question I have is that the colleagues in ALCF are very talented people. They wear many hats. They are computer scientists, but also they might be theorists. And they're also working on the topic. So when the data is coming in, and so they have the first peek at the data, so temptation is, they have to resist temptation of taking advantage of that. And also, sometimes the computer scientists look at the data, they might have to talk to the experimentalists to get an idea of how to tackle certain technical issues, how to process the data or something like that. So they might inadvertently given somebody else outside of the experimental group some information about the experiment. Experimentalists are very protective of the data. So I just wonder how you're going to protect that environment, make these wonderful things very safe for the experimentalists.
It's a good question. Yeah, and that has come up a lot in our discussions, right? So I think the answer is that in any context, you probably have an impulse to want to share, but not share too much, right? You may want to share with your collaborators, the same people on your experiment, same people on your team, but not with people outside of that sphere. And so security is a strong element of this, right? I think we start from a good place because within the compute facilities, we live already in a very secure environment. Again, see how easy or difficult it is to get an account, right? And the things that I didn't explicitly show this, but in terms of sharing your data via Eagle, for example, you can make that your choice, make that choice yourself in terms of what should be shared and with whom, right? So we, as ALCF, we will never make the choice that says your data is public and it's shared with everybody, right? But we give you that choice. And if you make it public and people access it who you didn't want to access it, then you would constrain that quickly, right? Right? Change the constraints a bit. I think that's we have these mechanisms in place and we know how important they are. So yeah, thank you for the question.
So one question I have is, given this effort for IRI, does this imply that like the things like the batch systems and, interfaces and things between the different compute systems will be converging towards something more similar. I spend a lot of time, I have an allocation at NERSC, I have time here at ALCF, and spend a lot of time sort of figuring out what's a little bit different and a little bit, flaky. Oh, I have to do it one way here, a different way there. And, that's a lot of mental effort that's not really always super useful. So if it's more familiar and more uniform, that would be a big deal.
Right, right. Yeah, that specifically, the scheduler is something that comes up in most conversations with users. And it's not only a matter of making your applications run at the 3 facilities in the 3 different systems, right? But then we have an upgrade. And so now things change again. And if you have multiple systems available, like we do here, then you're adapting between systems at one facility. I think there's a couple of ways of thinking about this, right? Having everybody use the same tech across all the compute facilities looks like a simple way to solve the problem. As a software, as a person coming from one facility who's talked to people from other facilities, it's unlikely that we will achieve that. As a software person, it looks like an obvious place for an abstraction layer, right? And so in the workflow tools, to some extent, we achieve that, right? We talk to the scheduler, you talk to the workflow system. And now you don't have to think about adapting your things for each particular site. To some degree, maybe you do, because you still have to put specific MPI launcher things in your scripts, right? We try to capture those things too. And honestly, it doesn't exactly help them when there are multiple workflow systems either, right? Because now we've just said, let's take the multiple schedulers and give you 3 abstraction layers to them, right? Maybe not exactly solving the problem, but you can choose one of them, have your single abstraction layer across schedulers, and I think that's the approach to solving that problem that we will take. And you can take your question and use it as a template for other areas that you have to think about when you're talking with a facility, right? Hopefully we'll come up with similar approaches there where we can abstract away those details.
So any other questions? Yes.
To begin with, thank you for your talk. It was extremely well organized and really interesting. So probably the biggest challenge we have at my group up in Milwaukee is organization. Like you mentioned data. They do in fact use data that is within the group. Accidentally, one doctor will accidentally clobber the data of another, things like that. What will happen? I'm wondering if it looks like I'm going to be the person that actually does the connecting to your systems for the foreseeable future, maybe a year or two, which is I'm happy to do it, but I will not be in that position for longer than 3 to 5 years. So how should I go about mitigating them clobbering each other on your system too? Does that make sense? The team accounts issue. So I can edit and I think the word would be proofread their choices, and then after I leave, how should I before I leave, how should I prepare them for that difference of exchange? should I be training them the entire time, or I have a number of questions I'd like to talk to you about, but I know you don't have all the
Right.
time in the world.
It's a good question. So I mean, I could, I sort of presented two forks, right? One is Nexus, which is what we're doing at ALCF, and the other one is IRI, which is this larger conversation that we're having about what that should look like. So answering your question about what you should do, planning for handing off work to somebody on a 3 to 5 year time frame, I think means, the answer I would like to give you is that anything you do should look like code in a repo that is reasonable and can be interpreted just like your application code could be, right? And the person you hand it off to could pick it up, you know, near the end of that time or whatever is the right time frame for you, right? To familiarize themselves with it and pick it up and be able to carry it forward. It should look very much like what you would do with your application code. There will, of course, be changes along the way, but there are changes in everything, right?
Thank you.
Sure, you're welcome.
Any other questions? No. So let's thank Tom again.